Last talk of this morning's session is given by Nikolay Korolev, analysis of structures and forces defining chromatin compaction.
Good morning, afternoon, everyone. And of course, I, as all the presenter, thanks organizer for allowing me to present here. And here are the Singapore Stockholm Consortium work. And I will be talking about analysis of structures and forces defining chromatin compaction. And since I'm under severe pressure of time, I will try to cut the introduction. You all know that chromatin should be compacted in very 46 of these chromosomes of this size should be fit into this eukaryotic nucleus in humans. The fully compacted DNA takes roughly the same size, so it should be mostly compacted, but at the same time dynamic and accessible to response to physiological signals and to the development needs. So on the level of the first level of eukaryotic chromatin organization, it's remarkably uniform and consists of linear arrays of nucleosome coparticles connected by linker DNA. And these linear arrays compacted further into multi-level organization structures, which are highly debated and discussed recently. So for me, as physical chemist, the problem of compaction of chromatin is the electrostatic problem, because DNA is one of the most highly charged polymers existing in nature, and it attracts a lot of counter ions close to the surface, and the entropy loss due to the confinement of these counter ions is a major thermodynamic factor which defines the behavior of chromatin. And to neutralize DNA charge and to cancel DNA repulsion, electrostatic, the histone proteins, they are highly positively charged, and the core histone organized part have charge about 52, and the most of the charge of the histone tails are in the histone tails. And it hints that nucleosome remains a highly negatively charged particle, and tail can form a function of neutralization and bridging. So I disagree with almost everything what Alexei Anufriyev says about the stability of this particle, but I will talk about the next level of organization. It's about then when chromatin condense, you have to have nucleosome-nucleosome contact, and this contact multiply, and the measurements of Bustamante and John Van Noort showed that the nucleosome-nucleosome interaction in physiological condition, it is attractive, and we have to find the forces and the structures which create this attraction. So the only order which can be seen in life in chromosomes and mitotic chromatin by, say, small X-ray scattering is the short range order, and it is the two contacts are visible in this in chromatin in vivo. That is the nucleosome stacking. It's just two coins on the top of each other, and edge-to-edge contact, the distances with characteristic distances 6 and 11 nanometers, and no higher order structures is observed in native chromatin. The nucleosome stacking is also very common in vitro studies. These are data of electron microscopy showing the stacking of chromatin into the 30 nanometers, stacking of nucleosome in 30 nanometers fibers. Also, the nucleosomes in solution have a tendency to form columns where they stacked and slightly tilted relative to each other. And in the crystals, we have a nucleosome-nucleosome contact, which is also stacking. And these crystals are single nucleosome or tetranucleosome. They all show the close contact between nucleosomes. So how? So DNA is wrapped around the histone core in its form of superhelix, and it's natural to think about that to build So I want to analyze it in quantities, the geometry of DNA-DNA contact. So we need to build a coordinate system based on DNA, then to describe this, how these two coordinate systems interact to each other. So natural choice is use the symmetry of DNA superhelix with characteristic diameter and the helix axis, and characterize the plane of the NCP by the plane which is perpendicular to the helical axis. But it looks not good because this plane cuts through the DNA on the edges, and it misrepresents the orientation of plane. So we suggested to create a new system, coordinate system, which characterizes the form of this wedge-shaped cylinder better. So I use the center of the mass of organized part of the histone core, and this will be the center of the symmetry of the nucleosome. Then I define the polarity of this cylinder on the lateral stuff using the sequence. If it is 146 nucleosome in the base pair in the DNA, then I use central 73, 74. Two base pairs. If it's 145, then I use one base pair. Center of the mass of this base pair defines the symmetry axis, which is very close to the diad axis of the superhelix. And also I use different base pairs on the sides of DNA to define 2 points, which based on which and this diad axis I built the averaged the position of plane, and this is the vector is perpendicular to this plane. So now we have new coordinate system, and we can describe nucleosome-nucleosome interaction using this system. And it's a better presentation of the cylinder shape and polarity of nucleosome. So to define this, it's just geometry task. So we need to introduce first of all, nucleosome-nucleosome distance, then the rise, and then shift, because these coins can be shifted relative to each other, and shift orientation. Again, it is angle between symmetry axis and the line connected this projection of the center of one nucleosome onto the plane of the other. So also the very important characteristic is orientation of symmetry axis or diad axis, and it can be head to head and head to tail, and these cylinders are tilted relative to each other, and they have this tilt has an angle and the direction. So we have the set of the parameters. We define the nucleosome-nucleosome contact, and you can describe any nucleosome mutual nucleosome position using this coordinate system. So here are the examples of which exist in published crystal structures. This is the most common and widely known contact, which is the first atomic resolution crystal structure, and vast majority of all, about 150 now, crystal structures existed. They have a similar arrangement. Also, and they have a head-to-tail orientation and quite significant shift of the nucleosome relative to each other, and also very common in nature, but very rarely described in crystal. This is head-to-head orientation in tetranucleosome, which is characterized shorter distance and less smaller shift. Also, there are few crystal structures where the axis oriented head to tail, but the other parameters are similar to a tetranucleosome. And there are several, maybe now exceeding 10 or 20 crystal structures where nucleosome is complexed with proteins, and in these crystal structures there are no direct nucleosome-nucleosome stackings. And here is one of the example where the one nucleosome is look like this, and it is chromatosome, and somewhere here is the global linker histone. So we collected the statistics of all crystal structures and describes the parameters of this contact. And in the crystal structures, the most of them has the distance between nucleosomes about 68 angstrom, and the rise about 55. Angle is in the range 10-15 degrees, and they are quite shifted relative to each other, roughly by 2 diameters of the DNAs. And I think this sort of shift allows to avoid the DNA-DNA repulsion when the one DNA are on top of each other. So going into, there are, you can see that there are many possible nucleosome stacking structures. So what is responsible, and what rules can be deduced for the preferable orientation of the nucleosomes in the stack? So we guess that probably electrostatic nature of DNA and histone tails can play a role in this, in the formation of nucleosome stack. And as you can see, without tails, nucleosome remains highly negatively charged. And to address this issue, we model the behavior of nucleosomes using coarse-grained model, kind of without inverse Monte Carlo, using soft repulsive potential and description of coarse-grained DNA similar to the ones presented by Sasha and Thierry. And with flexible tails with resolution of one bit per tail, and with explicit charges both on DNA, on histones, and in solution. So we created these spiders and put 1, 10, 20 of these spiders into the can with different counter ions, neutralizing the excess negative charge by either potassium or magnesium or cobalt hexamine. And what we found that the coarse-grained system behaves very similarly to the experimental ones. Then when we have potassium neutralizing nucleosome charge, then nucleosomes repel each other, and they stay away all the time. When we have magnesium neutralizing excess charge, then the aggregates of 2-4 nucleosome forms, and in these aggregates, nucleosomes are stacked. And when we have cobalt hexamine, then we have effectively very loose cluster of 10 or 20 nucleosomes. And these nucleosomes are arranged in columns, very similar to the pictures observed in electron microscopy. And we can average the statistic over the simulation run and find that the kind of average orientation of the nucleosome in the stack, if we kind of describe the distribution of nucleosome by densities, then it is very similar to the ones which can be found from electron microscopy pictures. So we can go into further details, and just to merge together the data from coarse-grained simulations and crystal structures we analyzed using our new coordinate system. And here is the dependence of nucleosome distance on NCP and NCP shift relative to each other, where the points are the data calculated from the crystal structures, and the areas are statistics of our coarse-grained simulations. As you can see, shift is for the crystals kind of away from simulation data, but there are quite a lot of crystals which are close to the coarse-grained simulation. That shift probably caused by the necessity of the stabilized crystal and because of the crystal lattice. So more interesting is to consider the orientation of the axis in the stacked structures. As you can see, the simulations report that it is not, it is kind of smooth, but still there are 3 preferential positions of dyad or symmetry axis. It is head-to-head, the most populated in simulations, head-to-tail, and 90 degrees, which is, and for head-to-tail, we have most of the crystal data here, but few and most kind of in vivo relevant crystal structures, they have head-to-head orientation, which you expect from this concertina-like folding of nucleosome nucleosome fiber. And and we have also 90 degrees orientation, which is not found in experiment. So what is behind this quantum positioning of the nucleosome in the stack? So we think it is tails. We have in nucleosome, between nucleosome surfaces, we have 4 tails, 2 from each of the contacting nucleosome, one H2A, one H4, and the average distribution in simulation are shown here. And if you put one nucleosome onto another, you will find that to avoid the overlapping of the tails and effective shielding of the DNA in this contact, you have only selected positions. And you can rotate the one nucleosome relative to another by 90 degrees, and to have this, to avoid overlapping of the tails. So we guess that the tails define the most populated and energetically favorable nucleosomes orientation in the stacks. And also, simulation predicts that 90 degrees orientation could exist, and it is interesting to see if it is observed in nature. So I conclude my presentation that we created new nucleosome-based coordinate system, and it is kind of convention which I suggest to use as in this description of DNA stacking in DNA double helix. Also, we found we described all existing published crystal structures. And also we showed that coarse grain simulations are a very valuable instrument, and they confirm most of experimental observations. And we also showed that the tails are very important for formation of nucleosome stack and can define orientation of the nucleosomes in the stack. Thank you for your attention, and I hope I didn't exceed much of my time.
Thank you. A few questions.
Oh, the most important slide. So I am very thankful to our wonderful team, leading by Lars Nordenskiöld, and of course our 22 years collaborator, Sasha Lyubartsev. Without him, all this simulation stuff would be garbage. So, but I'm pretty confident in validity of our models because of the Sasha's background and deep knowledge. Thank you very much.
Very nice talk. I don't have a question, I have a comment. So I don't disagree with most of you say, but since this is not reciprocal, we should have a heated debate at lunch.
I would like to discuss the disagreements.
Bring your boxing gloves.
Yeah. Okay. Please.
Yeah, nice talk. But I'm now out of your field. But could you tell me again that what's the role of the tails, both from the viewpoint of the energy and from the point of the structure?
So you see that most attention is paid to H4, which is highly involved in contacting this acidic island in nucleosome stacks. But H2A so far avoid attention of the studies. But as you can see, these tails are of similar length. They have the similar charge, and distribution of the charges along the length of the tail are similar. So one can easily, and they geometrically very similarly positioning. So you can say that they can exchange and contribute together in this information of the nucleosome stack. And they just distribute and shield DNA charges, but they don't like to overlap in nucleosome stack. That defines the preferable orientation of the tail.
So after the stacking, the tails are located in the each way independently.
In between this.
Between them.
Between the contacted nucleosome, and they shield negative charge of DNA, and they are very dynamic. And this contact also increase the entropy, because they can sample in a larger space, not only close to its own nucleosome.
Okay, that's additionally stabilized?
Yes,
no?
the bridging mechanism is just it's similar to bridging mechanism. The bridging mechanism is the major contribution is entropy, because now the flexible tail is confined not only to its own DNA, but also it can contact the space, and it will increase entropy. Bridging is about entropy.
Yeah.
Okay, thank you, and we can close this morning session to have reasonable time for coffee break. So thank you.